Hello everyone, welcome to this session. Now in this session we are just going to discuss the chapter that is moving charges and magnetic field. At the starting of this we are just going to understand that what is a magnetic field. For that case we are just going to take an example of a magnet. We are having a bar magnet and it is having two poles, north and south. So if we are placing a magnetic needle very close to that of magnet, what it will show? It will show the direction like that. From the north pole, as the magnetic field lines are emitting and it is ending at the south pole, so the magnetic needle is showing the direction like that. As the magnetic field lines is emitting from the north pole and it is coming towards the south pole, and inside of the magnetic field lines are from north pole towards the south pole. So the magnetic field lines will look like this, right? These are in the form of concentric circles, that means a complete circle. So the magnetic field lines are produced in this case of bar magnet. So we are just going to understand the next concept, that what is the magnetic effects of current. Now with the help of Oersted experiment, we are just going to understand that what is the magnetic effects of current. For that, what we'll do, we'll just take a circuit, a simple circuit, which consists of a source voltage, a switch, and obviously a current conducting wire. So in this case, the current is flowing like that. So if the current is flowing through that of conducting wire, so in that case, we are just going to use a magnetic needle. And if we place that magnetic needle very close to that of conducting wire, what it will show? The magnetic needle will be deflected. That means it will show the direction like that. That means it will align itself as north south. Why it is aligning itself like that? Because when the current is flowing through that of conductor, the magnetic fields are produced in the form of concentric circles, right? The magnetic fields are produced in the form of concentric circles. So we have placed the magnetic needle very close to that of conductor. So the magnetic needle is in the magnetic field of the conducting wire. So that's why it is being deflected. Even the source voltage, if the source voltage is being reversed, so in that case the magnetic needle will be deflected in the opposite direction. If we increase the current, so in that case the magnetic needle will go closer to that of conducting wire, right? And the deflection will also be increased. So that experiment was done by Oersted, that shows that what is the magnetic effects of current. That means if some current is flowing through that of conducting wire, some magnetic field is produced, and in that magnetic field, if a magnetic needle is placed, it will be deflected, right? Now we are just going to move to the next concept. So our next discussion topic is Biot-Savart's law. In that case, what we will consider? We'll just considering a current carrying conductor like that. So in that case, the current is flowing in the upward direction as I. So in that case, we're just considering a very small portion of that wire as a DL, right? So through that the current is flowing, so it will form a current element, and due to that current element, we are just going to find out the magnetic field very close to that of wire. Suppose at this point, we are just going to find out the magnetic field. Okay. So what we'll do, we'll just join a line to that of point. In this case, it is having the distance of R. Okay. So if the current is flowing in the upward direction, so obviously some magnetic field will be produced in the form of concentric circles, right? So in that case, we are just going to find out the magnetic field at this point P. In this case, there is an angle that is of theta, right? So whatever the magnetic field is will produced at that of P, it will having some direction. It may be of clockwise, it may be of anti-clockwise. We'll definitely understand that in which direction the current uh, we'll definitely understand that what will be the direction of the magnetic field later. So in that case, the magnetic field produced at this point P is directly proportional to the current flowing through that of conductor. It is directly proportional to that of small portion of the wire through which the current is flowing. and it is proportional to the sine of the angle between the length of the element and the line joining to that of point P, right? That means it is proportional with that of sine theta. And the magnetic field is inversely proportional to the square of the distance between them. Right? So if I can accumulate all these expressions, what the expression we are getting finally, that is dB is directly proportional with that of IDL sine theta divided by of r square. So why the magnetic field is inversely proportional with that of distance? Because if you are going closer to that of conducting wire, you will get more magnetic field lines, and if you are moving away from that of conductor, you will get less magnetic field lines. So in that case, the magnetic field is inversely proportional with that of square of the distance between the point P and the conductor. So we are getting a expression for that. So it is a proportionality. So to break the proportionality, we should introduce a constant that is of mu naught by 4 pi IDL sine theta divided by of r square. That will be the final expression, right? So that expression can be written in the form of in vector form also, as magnetic field is a vector quantity. So it is equals to mu naught by 4 pi I, and here the dl and the r, and it will be of r cube, because in this case the current element is actually a vector quantity, so it can be written like that. Okay, so now we can find out the Biot-Savart law in the form of current density as well. We can introduce that term because we know that current density J equals to I by A. That means the current flowing through a cross-sectional area. So if I just multiply dl in numerator and denominator, what it will form, that it is equals to idl divided by of cross-sectional area multiplied by that of length, that is equals to the volume. The childhood formula, that cross-sectional area multiplied by of the length, that is equals to the volume. So in that case we are just getting an expression that J current density equals to IDL by of dV. So I'm just writing down that expression in the next page. If J equals to IDL divided by of dV, so IDL that is equals to J multiplied by of dV, right? So in that case, the magnetic field will having the expression as mu naught by 4 pi J dV sine theta divided by of r square. So even we can write down that one in vector form, as dV vector is equals to mu naught by 4 pi J vector cross of r vector divided by of r cube, and here the dV will be there, right? So this is the Biot-Savart law in the form of current density as well. Now we are just going to move the next topic. So there are certain rules to determine the direction of the magnetic field. Rules to determine the direction of magnetic field. How many rules we are just going to understand? The first one, that is a right hand thumb rule, right? What is a right hand thumb rule? Suppose if we are using a conductor, suppose in that case you are just holding the conductor on your right hand and the current is flowing through that of conductor in the upward direction. So in that case, if you just curl your fingers like that, if you just curl your fingers like that, so you will get the direction of the magnetic field. Now when the current is flowing in the upward direction, you will get the magnetic field like that. That means in anti-clockwise direction, and the magnetic field lines will be in the form of concentric circles like that. Okay, so according to right hand thumb rule, what I can say, that there is the statement of that. I'm just going to tell you about the statement. I'm not writing that. That if we grasp a straight conductor in our right hand such that the thumb points the direction of the current, and if we curl our fingers, then it will show the direction of the magnetic field. Okay, so in that case the magnetic field is in anti-clockwise direction. Now if we are um, now if you are taking that conductor and the current is flowing through that in the downward direction, so in that case we will get the value of the magnetic field, and the direction of the magnetic field lines will be showing the direction in the clockwise. That means the magnetic field lines will be in the clockwise direction. You have to do the same, just you have to place your thumb in the downward direction, as it will show the direction of the current flowing, and the magnetic field lines will be determined if you just curl your fingers, and in that case, that means in the second case, it will show the direction as clockwise. So in the first case we were getting the direction as anti-clockwise, in the second case we were getting the direction as clockwise, right? So this is the right hand thumb rule. Now we are just going to understand that what is right hand palm rule. So what is right hand palm rule? Now this is the next topic, that is of right hand palm rule, and we are just going to determine the direction of the magnetic field with respect to this rule. So for that case we need the right hand palm. So I am just drawing the diagram. So I am just able to draw this diagram. This is actually a right hand palm. So in that case we are just stretching our right hand palm in such a way that our thumb is showing the direction of the current flowing, and our fingers is showing the direction to which point, that at this point we are just going to determine the magnetic field, and the point is P. So the magnetic field will show the direction perpendicular with that of our right hand palm. So in this case I am just telling you the statement again. So if you stretch your right hand palm in such a way that the thumb points to the direction of the current flowing, the fingers showing the fingers are pointing out towards the point P, at which you are just going to determine the value of magnetic field, sorry, the direction of the magnetic field. Then the perpendicular drawn with respect to your palm will give the direction of the magnetic field. So in this way the right hand palm rule can be utilized. So our next topic is Maxwell right hand screw rule. So in that case what it is told, that if we hold our screwdriver in our right hand and if we rotate it in such a way that screwdriver moves to the direction of the current. Suppose the current is flowing in the downward direction and the screwdriver is also moving in the downward direction. So your thumb will also your thumb will show the direction of the magnetic field, right? Suppose if you practically experience that one, that means you are using the screwdriver and you are just rotating that, then your thumb will show some direction. In this case, if the screwdriver is moving to that of downward direction, that is the same direction of the current flowing, then your thumb will show the direction, and that is clockwise in nature, right? That is clockwise in nature. So the magnetic field lines will be in the form of concentric circles, and they show the direction clockwise. Similarly, if you are just moving your screwdriver in such a way that it is moving in the upward direction, so in that case your thumb will show the direction of the magnetic field lines in the anti-clockwise direction. So if you draw the magnetic field lines in the form of concentric circles, and if the current is flowing in the upward direction and your screwdriver is also moving in the upward direction, then in that case your thumb will show the direction in anti-clockwise, and the magnetic field lines, it will be in the form of concentric circles. Now I'm just going to tell you some of the things about the direction of the magnetic field lines. So in that case, if the magnetic field lines is going into that of paper, in that case, suppose I am just drawing the magnetic field lines for this diagram. So in that case, the two portions I have just drawn over here. So it is showing the direction actually anti-clockwise. If I see the left side, and it is showing the direction of clockwise if I say the right hand side of the magnetic field line. So in that case, if the magnetic field lines is going into that of paper, right, so it will be represented by a cross. And if the magnetic field lines is coming towards you, so it will be represented by a dot. Remember this concept, that if the magnetic field lines is going into that of paper, that means it is going away from you, so it will be represented by cross. And if the magnetic field lines is coming towards you, so it will be represented by dot. Okay, so now we are just going to understand the next concept, that is the first application of Biot-Savart's law. So in that case, we are just going to understand the first application of Biot-Savart's law. For that case, we'll just take a straight current carrying conductor, so that through with that of current carrying conductor, some current is flowing with a magnitude of I. So in that case, we are just taking a small portion of the wire, that is of dl, and if the current is flowing through that of small portion, so it will form a current element. So due to the current element, we are just going to find out the magnetic field at this point, and this is P. So we are just joining a line with respect to that. So there is an angle of theta, right? So in that case, if we are just placing a distance over here also, so the distance of the current element with respect to that of point P, that is represented, suppose it is represented by R, and in that case the perpendicular distance, it is represented by A. So the angle that is equals to 90 degree, and there is another angle that is equals to phi. Suppose we have assumed that. So in that case, what will be the value of the magnetic field at this point P? So the magnetic field at this point P is represented as dB equals to mu naught by 4 pi IDL sine theta divided by of R square, right? So in that case, it is a right angle triangle. So I can say if that angle is 90 degree, so phi will be equals to 90 minus of theta, or I can say theta will be equals to 90 minus of phi. So what I will do, I will just going to substitute that value in that of expression, and it will be mu naught by 4 pi IDL sine of, in the place of theta I am just placing 90 minus of phi, and R square will remain same, and we are just getting that expression mu naught by 4 pi IDL sine 90 minus of phi, that is equals to cos phi, and R square will remain as it is. So now what we are just going to understand, we are just going to find out the value of the magnetic field. So for that case, we will integrate that expression, but we will integrate it with the help of some limits. That means for that of where we are just joining this portion, suppose if we are joining this portion with that of point P, so they will also form some angles. If we write down that tan phi, it is equals to L by A, right? So if we cross multiply, so L is equals to A tan phi. So we are just taking the differentiation on both of the sides. So if we differentiate on both of the sides, what we will get? We will get dd phi of L equals to dd phi of A tan phi, right? So in that case, it is equals to how much? It is equals to dl d phi, it is equals to A, and dd phi of tan phi, right? We are just getting that expression. Now we are just moving to the next page, as dl d phi, it is equals to A, and dd phi of tan phi. So dl d phi is equals to how much? A multiplied by of dd phi of tan phi, it is equals to sec square phi. So dl is equals to A sec square phi d phi, right? We are having that expression. Now I am just going to substitute the value of dl in the previous mathematical expression. That is, dv is equals to mu naught by 4 pi IDL cos phi by of R square. I'm just going to substitute the value of dl over here. So dv is having the expression as dv is equals to mu naught by 4 pi I dl cos phi divided by of r square. So in that case, it is equals to mu naught by 4 pi I dl cos phi. Sorry, in the place of dl, I am just going to substitute that value. dl is having the value of a sec square phi d phi, right? A sec square phi d phi, and there is already a cos phi is present. So, and here it is about r square. So we are getting the expression as mu naught by 4 pi multiplied by of I and the a multiplied by of sec square phi multiplied by of cos phi. So it is equals to how much? Sec square phi multiplied by of cos phi. We are just getting as sec phi d phi divided by of r square, right? So in this case, we are just getting that expression that mu naught by 4 pi I multiplied by of a sec phi d phi divided by of r square, right? Because one of the sec phi is getting cancelled out with that of cos phi. Now we are going to substitute another expression. So I'm just moving towards the previous slide. In that case, if this is the angle that is equals to phi, so what will be the expression of cos phi with respect to that? I can write down that cos phi, it is equals to base by hypotenuse, so it is equals to a by r, right? So in that case, I can write down that a by r is equals. So here cos phi is equals to having the value of a by r. I'm just going to substitute that value in that expression. So in this case, if I just multiply with a on both of the in numerator and denominator, the expression will be mu naught by of 4 pi multiplied by of I, and a is multiplying on numerator and denominator both of the cases, that is of a square, and it will be a r square multiplied by of sec phi d phi. Now a square by r square, I can write it down that one in a simplest form, that is of mu naught by 4 pi I by a multiplied by of a by r that whole square and sec phi d phi. Now here a by r, what do you know about cos phi? Cos phi is equals to a by r. So in that of a by r, I am just going to substitute the value of cos phi. So the expression for dv, that is equals to mu naught by 4 pi multiplied by of I by a multiplied by of cos square phi into sec phi d phi, right? So in that case, what will happen? So one of the cos phi will be eliminated and with that of sec phi, and I will get a final expression as mu naught by 4 pi multiplied by of I by a into cos phi d phi. So it is equals to db. So I am just going to take the integration on both of the side. It will be from 0 to b, and it will be from minus of phi 2 to that of phi 1, and in this case mu naught by 4 pi multiplied by of I by a will be comes out from the integration, and we are having minus of phi 2 to phi 1, and it will be cos phi d phi. So what we are getting, mu naught by 4 pi multiplied by of I by a integration of cos phi, that is equals to sin phi. It is having the limits from minus of phi 2 to that of phi 1. So if we substitute all the values in that expression, so what we are getting, mu naught by 4 pi multiplied by of I by a, the sign of upper limit should be substituted at first. minus of lower limit, that is of sine of minus phi 2. Okay, now I'm just doing the left hand side also. Integration of dv, that is equals to b, it is having the limits from 0 to b. If upper limit is substituted, it is equals to b. So magnetic field is having the value, now magnetic field is having the value of mu naught by 4 pi, sorry, it is just moved to the next previous slide, multiplied by of I by a, and it is equals to sine of phi 1, and it is of sine of minus phi 2, right? Sine of minus phi 2, it is equals to minus of sine phi 2. Okay, so if I write down that, it will be the plus of sine phi 2. So this is the expression, that is of mu naught I divided by of 4 pi a sine phi 1 plus of sine phi 2, right? This is the expression for the magnetic field. Now the derivation is so long, right? Now in any of the book they will not show you the derivation, but I hope you should understand that how the expression have come. Okay, this is actually the way that we are able to determine the value of magnetic field at that point. That means we are having the value of magnetic field at this point of P, and in this case, as the current is flowing in the upward direction, the magnetic field will having the direction as anti-clockwise, right? It is having the direction of anti-clockwise. So in that case, if you draw the magnetic field lines with respect to that of point P, so it will be like that. This is the direction of the magnetic field in the form of concentric circle. They will show the direction as anti-clockwise. Okay. Now we are just going to understand the magnetic field at the axis of a current carrying loop. Right. Now I am just going to make that diagram, that magnetic field on the axis of current carrying loop. So in that case, we are just going to make a current carrying loop at first. So this is actually a circular loop, so through which the current is flowing, obviously. So if the current is flowing through that of circular loop in that direction, then in that case also I am just taking the direction of the current as anti-clockwise. So in that case also I will just take a small portion of that of loop as a dl, and this is actually form a current element as idl. So this is the center of the loop, and there is a point on the axis of it at which we are just going to determine the value of magnetic field. So I am just drawing a line with that of point P, and this is the radius of the circular loop. In that case, I am just taking the radius as A. In this case, the distance is equals to R, and that angle I am just taking as theta. In this case, that angle I am taking as phi. As you know, this is actually of 90 degree. So what we know about from our Biot-Savart's law, that the expression of magnetic field at this point P, that is equals to mu naught by 4 pi I dl sine theta divided by a r square. Now I am just telling you some important property with respect to the tangent of a circle. Now the tangent is always having an angle of 90 degree with respect to that of radius. So in this case, this is the radius, sorry, in this case this is the radius a, and this is the value of tangent. That means I'm just talking about the line joining the current element and the point P. So theta is having the value of 90 degree here. So in this case I can write down that mu naught by 4 pi I dl, it will be of sine 90 divided by of r square, right? So I will write down that expression. It is of mu naught by 4 pi I dl divided by of r square, right? So in this case, the magnetic field will show the direction like that. With respect to that point, I'm just drawing it with respect to another ink. So the magnetic field in this case, it is showing the direction like that. If it is the magnetic field, so obviously I can say that with respect to this line, if I draw a perpendicular line with respect to that, this angle will also be equals to phi. So this is actually our dB cos phi. So by symmetry, I will get the dB cos phi in that direction also, right? And this is the direction of dB sin phi. So as you can see, we are getting the magnetic field due to only dB sin phi, as dB cos phi is cancelled out by symmetry. So you have to find out the value of dB sin phi to get the value of magnetic field. Now, in that case, what you have to do, that the distance of the center, I'm just naming that center is O, the distance between the center and the point P, that is equals to x. So I can write down that r square is equals to a square plus of x square, right? Now what will be the value of sine phi from this expression? Sine phi is having the value of, I'm just writing down over here, sine phi is having the value of perpendicular by hypotenuse, that is, it is equals to a by r. It will be used in that of expression. So I'm just giving you that value. So we are just going to integrate the function of dv sine phi only, so that we will get the value of magnetic field. As you can see that dv sin phi is only give you the value of magnetic field over here. So I'm just moving to the next page. So B is equals to the magnetic field, and it is equals to the integration of dv sin phi. So dv is having the value of mu naught by 4 pi I dl divided by of r square, and sin phi is having the value of how much? Sin phi is having the value of a by r. So I am just going to substitute that value, that it is equals to a by r. So it is equals to how much? Integration of mu naught by 4 pi I dl a by of r cube, right? So RQ is R is having some expression. In the previous slide we can see that R square is having the value of a square plus x square. So R is equals to root over of a square plus x square, right? As this is a right angle triangle, so we can write down it. So in the place of R, we're just going to substitute that value, that mu naught by of 4 pi I dl multiplied by of a, and it will be root over of a square plus x square, and it will be of whole cube, right? So what can I say? That it is equals to integration of mu naught by of 4 pi I dl multiplied by of a divided by a square plus of x square. Root over means actually root over of a square plus x square. It is equals to a square plus x square whole to the power of half, right? So I can write down it is having a power of 3 by 2. So in that case, what can I do? That is, we are having that expression. So now we can write it down that it is of mu naught divided by of 4 pi I dl, sorry, dl will not comes out from the integration, a divided by of a square plus of x square whole to the power of 3 by 2 integration of dl, because in this case dl is one type of operator that will be of inside that of integration, and maximum of the constant terms that will be of comes out from that. So integration of dl, that will be of how much? Integration of dl, that will be of, we are just writing down, that is of mu naught by 4 pi multiplied by of IA divided by of a square plus x square whole to the power of 3 by 2, and integration of dl is actually L, and L is actually the 2 pi a. This is actually the circumference of the circular loop. Okay, so I'm just doing one small step jump over here because we are not having any space. So we are getting the final expression like that. I'm just simplifying that expression in the next page. Now let me tell you about one thing that I hope there is some problem in understanding that one, that integration of dl that is equals to L. L is actually the total length of that circular loop, that is actually the circumference. So that's why I have written it is equals to 2 pi a. Okay, so now we are just moving to the next case. That is of we are having the expression that in the previous expression some of the things can be eliminated. 2 pi can be eliminated as it is equals to 2. So we are having the expression as mu naught I a square divided by 2 into a square plus x square whole to the power of 3 by 2. Right? We are having this expression. So this is the expression for the magnetic field on the axis of a circular loop. Now, in this case, if it was told that you have to find out the magnetic field at the center, what you will do? That the magnetic field at the center of the circular loop, magnetic field at the center of the loop, that is equals to how much? That means x will be 0. In this case, the distance from the point that will be equals to 0. So in this case, if x is equals to 0, I will get the expression as mu naught I a square divided by of 2 into a square whole to the power of 3 by 2. So in this case, 2 is eliminated. So I will get the expression as mu naught I a square divided by of 2a cube. In this case, these 2's are eliminated. So a square is eliminated with respect to that, and I'm just getting the expression mu naught I divided by of 2a. Mu naught I divided by of 2a. This is the expression of the magnetic field at the center of that of circular loop, right? Now we are just going to understand the next part, that is Ampere's circuital law. So in Ampere's circuital law, what we are just considering that it is very much similar with that of Gauss law in electrostatics, because in both of the cases we have to assume a closed path. Suppose you are having a conductor, a current carrying conductor through which the current is flowing like that, and you are just considering the magnetic field as like that. It is in the form of concentric circles. So in that case, if I take the line integral of the magnetic field, as you can see the magnetic field is showing the direction as anti-clockwise. So if you take line integral of the magnetic field, that small portions are added up. If small portions are added up, then you will get the total current enclosed by that path, right? So the line integral of the magnetic field around any closed path is equals to mu naught times the net current enclosed by that path. It is actually told by Ampere, and we can formulate it as closed surface integration of B dot dl, that is equals to mu naught multiplied by of I. Here B and dl both are the vector quantities. Okay. So in that case, if it is a circular loop, what can I say? That B will comes out of the integration, and I will get closed surface integration of dl. It is equals to mu naught multiplied by of I. So what we are getting? B multiplied by of dl. So it is having a radius also. In this case, we are just taking the radius as r. So integration of dl, that will be of 2 pi r, and it is equals to mu naught multiplied by of I. So B is having the expression as mu naught I divided by of 2 pi r. Okay. So in that, with the help of Ampere's circuital law also, we are able to calculate the magnetic field, right? So now there are different applications of this Ampere's circuital law. Remember in the class also we have just done the proof of this Ampere circuital law. I'm not discussing all of the things. I'm just giving you a brief of this chapter. Okay.